Welcome to Ask and Learn.
We are given sets, and we are asked to find a deterministic finite state automaton that recognizes each set. So in part A, we're given the set 0. Now, since this is an automaton, we have to have a start state as 0. Now, because lambda, the empty string, should not be recognized, it follows that S0 is not a final state. Now, suppose that the string starts with 0. Then we see that the string should be recognized, so we'll want to move from the non-final state S0 to the final state S1. And if the string contains any more bits, then we'll want to move from the final state to a non-final state. So suppose there are any more bits, then we'll move to the non-final state. In this case, we don't want to move back to S0, because if we were to do that, then we would have that, say, the string 0, 0, 0 would be accepted, which we don't want. So move to a new non-final state, S2. And once we're at S2, we should not be able to escape because the string can never be recognized. So we will remain at S2 for any input. Now, on the other hand, suppose that the string starts with a 1. Well, in this case, we have that 1 should not be recognized, so we should move from S0 to the non-final state S2, and as before, we're going to remain at S2 for any input. And this concludes the description for the deterministic machine. In part B, we're given the set 1, 0, 0. Now, once again, let S0 be a start state, which we know must exist. Since the empty string is not contained in this set, it follows that S0 is a non-final state. Now, suppose that the first bit is a 0. Well, we see that this string should not be accepted so far, but it has potential to be accepted. So we want to move to a new non-final state, otherwise the string 0, 0 would not be accepted when it should be. So we'll move to non-final state S1. And then once we're at S1, suppose that the second bit is a 0. Well, we'll want to move to a final state S2. And we see that if there are any more bits, then the string should not be accepted, and we should move to a non-final state. And this can't be the same at S0 because this would imply that a string like 0, 0, 0, 0, 0 would be accepted when it's not. And we can't make this the same as S1 because this would mean that a string like 0, 0, 0, 0 would be accepted, which is also not true. So we'll move to a new non-final state, S3. And we see that once we're at S3, the string can never be recognized, so we shall remain at S3 for any input. So that's one case. Now, suppose that the first bit is a 1. We see that 1 is accepted. So in order to have 1 be accepted, we'll have to move to a non-final state. To a final state. Now the question is, do we need a new state or can we use an old one? So looking at S2, if we were to use S2, would we have any problems? Well, notice that if there are any more bits at S2, we're automatically going to be trapped in the non-final state S3. And this is good because if there's any more bits after the 1, the string should never be accepted. So we'll keep the same final state S2 here. And following the same rules as before, if there's any more bits, then we move to non-final state S3 and remain there for any further input. And that concludes the finite machine for part B. Now in part C, we're given the set 1 to the n, where n is equal to 2, 3, 4, and so on. One second, actually. So, once again, we know that there must be a start state. Let S0 be the start state. Now, since the empty string is not contained in this set, it follows that S0 is a non-final state. Now, suppose that the first bit is a 0. Then we see that we'll want to move to a non-final state. And we don't want to stay at S0 because this would imply that a string like 0, 1, 1 could possibly be accepted, which is not the case. So we'll want to move to a new non-final state, S1. And we see that we will remain at S1 for any input, since the string can never be recognized at this point. Now, on the other hand, let's suppose that the first bit is a 1. Well, the string still shouldn't be recognized, but there's a possibility that it could become 1, 1, which can be recognized. So we want to move to another non-final state. This should not be the same as S1 because we don't want to be trapped, and it shouldn't be the same as S0 because this would imply that once again we'd be trapped at S0, or if we had a 0 after that we'd still go to S1. We would never have any final states, which we know is not the case. So we move to a new non-final state, S2, and suppose that the second bit is a 0. well then this string is going to be 1, 0 and should not be accepted, and in fact can never be accepted. So we'll want to move to the non-final state S1, and just as before, we will be remaining there for any further input. And suppose instead that the second bit was a 1. Well, in this case, we're beginning with 1, 1, and the string 1, 1 should be accepted. So we should move to a final state, which is going to be a new state S3. Now we see that once we're at S3, if we suppose that the third bit is a 0, then we're going to want to leave S3 to move to a non-final state, and in fact want to stay in a non-final state. So we'll move to the non-final state S2, where we will be trapped for any further input. And now suppose that the third bit is a 1 instead. Then we'll want to move to a final state, and in fact we see that we can just move to S3 again. So we'll remain at S3. In this way, if we do have another 0, we'll still be moving to the non-final state S2, and the string still won't be counted. But we'll also be counting all the strings that are 1 to the n for n greater than or equal to 2. This concludes the construction of the deterministic machine.